Okay, so in the last class, we learned about some basic overview about IoT and how IoT is applied in different areas and the importance of IoT, the history of IoT, and the basic architecture of IoT, and so on. So today we'll be talking about further details about the IoT and how the physical design of IoT is defined, right? So what is physical design of IoT mean, right? So physical design of IoT refer to the hardware and the network protocols that are used to um, uh, create an IoT network. So in that IoT network, these hardware and network protocols will will enable the collecting of sensor measurements and help in the establishment of the communication between the sensors and the internet, right? Sensors-based devices and the internet, right? Basically, the IoT network can be divided into two categories. The physical design of IoT can be divided into two categories. So the first category is things. It's known as things, or we can call it as smart objects, right? We call things or smart objects, and they represent the hardware components that we use for IoT networks, right? So in order to design an IoT network physically, we need things and protocols. So things refer to the sensors, processors, communication modules, and so on. So these hardware devices, uh, the devices that help us to collect the data and process the data and communicate to a local server, which will then forward it to the cloud, is known as things, right? So the sensors that we use, the different types of sensors, the different microcontroller based hardware boards, then the communication technology based module that we are using in our system, in our edge of the IoT network, we call as things. The whole entity we call as things, right? And then next we have the protocol category, which relate to the standards and the rules that we follow to establish communication between the thing and the IoT network, right? So for that, we need to establish protocols basically in the link, in the physical and data link layer, the network layer, transport layer, application layer, and so on. So we'll be talking about these components under things and protocols in this today's lecture, right? So if you have any questions, you can put in the chat. I will try to answer your questions, right? Let's go ahead. So things in IoT. So as I said before, things in IoT refer to the physical devices or the logical entity of devices that represent uh, the uh, the entity that collect data, process data, and transmit the data to a local server that will collect the data and transfer it to the cloud, right? So these physical devices can be composed of sensors and processing board hardware processing boards, etc. Right? So the logical entities or the smart entities can have simple sensors up to complex machines and systems, right? So at the end of IoT network, we can have even like small sensors as well as big machines that um, that are like robots or industrial equipments, right? It could be like if you are working in automated industry, the robots can be moving, or the factories could be building something. That device uh, also is considered as a thing. So we can consider that also as a thing, and that device we can control using our IoT network, right? So in IoT, another thing I need to mention is about cyber physical systems. So like in IoT, actually, we are talking about actually simple sensors and simple actions at the edge of the network, right? So we can have access point, and then we can have sensors, right? So we do the communication to and fro from the access point to the sensors based processing unit, right? So this edge device can have simple sensors. Apart from that, as I said, we can have complex machines also, right? So in IoT, we have mostly like simple data collection at the edge, right? Simple data collection at the edge of the network. But in cyber physical systems, it is a more advanced version of the IoT, where we have like robots or some kind of like complex machines at the edge of the device, at the edge of the network, which will work according to our instructions, or else work according to their own instructions based on the data that they collect from the environment. So these cyber physical systems can automate big machines to work autonomously on their own in their environment, right? Based on their own data, and also based on the cloud-based instructions, centralized data, right? Centralized information or data that they receive, right? So cyber physical systems and IoT are actually two concepts, where cyber physical systems are actually a much more advanced version of IoT, where IoT is simply actually collecting data and transferring the data to a cloud network, where the cloud network is doing all the calculations and the processing, right? So uh, so we were talking about the things in IoT. So in things in IoT, these things that we consider as the sensors plus the processing board plus the communication modules uh, can consist of small sensors, simple sensors, up to complex sensors, and even have like machines or actuators inside them, actuators comprised in them. Okay, so these things need to have a unique identity. That means each device that is connected to the IoT network should have an address, like a unique address that it can be uniquely identified. So each device is given an IP address, right? So once they are communicating over the network, the data will be communicated using these addresses, right? So they have their address, and once the access point is like receiving this data, it knows to what destination it needs to forward the data. And also once the data is coming in the reverse direction from the cloud to the device, this IP address is used to transmit the information reliably to each unique device. And therefore we need to have uh, each thing or the smart object, each thing must have a unique identity IP address. And we can have remote sensing at the thing, right? At the thing, we can have sensor measurements, actuating, monitoring done. So that means that actuating means that there are some motors and some valves and some kind of mechanical process going on at the thing, at the edge of the device, at the edge of the network, that can be automated using our IoT network, right? And then also we can do environmental monitoring using several sensors. We can do some monitoring about our environment at the thing. Then this device also can communicate with other devices, and the local the access point, and then the it can have connection with the cloud. So so the thing devices, they can use technologies such as Bluetooth uh, and other short range communication technologies to communicate with another module directly without the authorization of the network, I mean centralized server, right? Without the centralized server, it can communicate within each other using short range communication technologies such as Bluetooth, that they use another like frequency spectrum to communicate, right? So yeah, the difference between remote sensing and monitoring. So yeah, so sensing means like collecting data using sensors, and then monitoring means like if the device is monitoring its environment, then that means they are doing some process at the edge, at the thing, at this location itself. It is doing the processing. That means if they are doing the processing here itself, we can call it as monitoring, right? For example, we can take one example where we are monitoring the water quality, for example, water quality of a certain environment using some sensor, right? If that sensor is doing some calculations and collecting data over time, and then seeing that the pH value of the water is above a certain value, right, above a certain threshold, then it will communicate to the access point, right? Or else it will not do anything. It will be in sleep mode. That means it will not communicate with the access point, right? Otherwise, the another way is that the sensor can collect information and send all the data to the access point. That means sensing only, not doing any processing. So then we can just call it as remote sensing, just sensing and then not doing further processing. But monitoring means like they can do the monitoring at the processor, and then it can make decisions at the processor, and then it can give valuable information after after taking some uh, constraints and into account, and then it can transfer only the valuable information, right? So they are almost similar tasks, but we can consider that this sensing is not that much doing any complex task, but in monitoring, we can do the monitoring at the environment itself and make some decisions. So afterwards, yeah, so as I said, the things can process either locally or remotely. That means the things can process at the local at the access point based local server, or at the that means they can process in the centralized location, right? Or else they can process at the edge or at the thing at the device level, right? So they can do processing at the device level or processing at the server level, right? So the data that is used, the collected is at the thing is transmitted to the cloud or the central processing system, right? So basically thing is anyway collecting data, maybe it is making some decision, and then it is transmitting data to the cloud or the central processing system. So we can have multiple sensors in IoT networks. So some examples of sensors are these light dependent resistors, where where we can detect the sensitivity of the light, and then based on the sensitivity, the resistance of the LED will change, and based on that result, we can do some, we can apply it for applications where we can turn on a light based on the light sensitivity. If the light is not enough in the environment, then we can turn on lights in that area, right? And then we have passive infrared sensors, right? Passive infrared sensors are used to detect IR radiation or infrared radiation in the environment. So infrared radiation is mainly found in like organisms, like it is used to detect heat in the environment. So these PIR sensors are known to like detect the existence of humans or animals in a certain area. So that is one application. So they can be used for fire alarms, like thief detections, and so on. So these uh, sensors can be used in indoor environments because it is easier to detect the heat, specifically in uh, indoor environments, right? So depending on our application, we need to select the correct sensor for our application, right? So there are many sensors that we can use, and depending on the IoT project or IoT application that we are trying to implement, we need to select the best sensor for our system, right? So if we are going to like detect smoke, right? For example, forest fire or fire in some area, or if we want to detect fire alarm, if we want to activate a fire alarm, we can install a smoke sensor that can detect the quality of the environment and detect the amount of carbon dioxide and the other gases that are generated during fire. um, these kind of smoke sensors can be used for such kind of applications, right? So they can sense the quality of the environment, yeah, as well. So the temperature sensor we can have for detecting temperature in different environments. So depending on the environment, we need to choose a specific sensor that we need to use. right? For example, if we have extreme temperatures, we need to use not the maybe not the usual temperature sensors, but we need to use some specific sensors depending on the application. And then ultrasonic sensors, they are using ultrasonic signals to detect objects in the close by environments, right? So they are basically using the concept called time of arrival, right? Time of arrival. That means that they the one of the transmitters in this ultrasonic sensor, right? One of them, let's say this one, it is sending the ultrasonic signal to the environment, and once it hits an object, it reflects back towards the sensor, and then the time it takes for the signal to reach back to the sensor is measured, and then using that time difference, we can calculate the distance to the object, because we know the frequency and the velocity of the signal transmitted. So using the uh, calculation of time of arrival, we can calculate the distance between the two objects. So the ultrasonic sensor is used for object detection. So we can check whether some object is there in a certain environment using ultrasonic sensors, right? The same principle that is used in radar systems, for example, right? Where we send a radar signal, and the radar signal is getting reflected back towards us. We can find like where a ship or some large object is there in the environment. The same principle used in ultrasonic sensors, and it's very useful when we want to apply it for applications where we want to identify close by objects, right? For example, if we are going to implement an autonomous robot, the robot needs to identify the objects around it. So in order for to do that, the robot needs to constantly send signal to its surroundings, and then try to find, okay, what is the object nearest to me, and then estimate the uh, best amount of distance that it can go forward. So likewise, we can use these sensors in different applications, that such that we can implement our autonomous activities. And then we have the phone, right? The phone is having, as I said before in our last class, we have so many sensors in the phone. So in the like newest phones, we have like near field communication uh, enabled technology in our phones, right? So near field technology is working with a certain frequency, and it is used for short range communication, right? In our phones, most of our phones, we have this near field communication technology, and it is used in many countries to make contactless payments. So also it is enabled with two-way communication. That means like once we send a signal to the other device from our near field communication chip, uh, and its antenna. We have an antenna in the near field communication chip, and then the receiver will send back a signal, and this near field communication chip is able to receive it. So because of that, it is known as near field communication technology is a more secure technology than RFID, QR code, and so on, right? Because near field communication has the two-way communication. It is known as a more secure way of communication because it can provide, the receiver can provide some acknowledgement messages to the device. So based on that acknowledgement, the user device can also authorize the transaction. So you can refer about this near field communication in the internet, and you can see that it is used for payments which are done very securely using NFC technology. So that is one technology that you can find in the phone. And then we can have other sensors like proximity sensors, magnetometers, like magnetic field measuring sensors. So accelerometers, humidity sensors, gyroscopes, moisture sensors, microphones, fingerprint sensors, barometer sensors, thermometers, touch screen, light sensors, GPS, pedometers, camera, and so on. So with the time, we are actually including more and more sensors into the smartphone to make it more powerful, such that it can have a really good information uh, in itself, and it can communicate it to a internet, and then gain more information about its location, for example, right? So which will make the life easy. So we can talk then about now we have talked about the sensors. So next, as the second kind of main hardware component, we can talk about the microcontrollers that we can use basically in IoT networks. So there are multiple types of hardware microcontroller boards introduced in the world. So there are many popular ones out of them. So Arduino Uno is a popular microcontroller board, and Node MCU is another one. Raspberry Pi is also very popular. Then we have ESP32. Right, so we can talk about all these things in the next slides. So all these microcontroller boards have um, mainly like they have power supply units, right? We need to supply some certain voltages, and we need to give certain specified voltages for the input output, right? So those things are mentioned in the technical specifications of the microcontroller boards. We need to follow those like voltages accurately in order to make the controller function smoothly and without causing any disturbance to the microcontroller functioning. We also need to have communication modules in those controllers in order to send the data wirelessly or wired communication towards a local server and then to the cloud computing platform. So we need to have a communication module. So most of them have some sort of a communication module installed in them. And then we have a processing unit in there. So we have to do some processing. We need to collect some data. We need to store them. So all that needs to be done. So processing unit must be there. And then storage unit. So some amount of storage unit must be allocated in the microcontroller board. So apart from that, we need to have input output pins where we need to collect some sensor data, and then we can also output the received data to the microcontroller, and then maybe to the communication module. So we need to have basically all these units: power supply, communication, processing, storage, input output pins in our microcontroller boards. So we will talk about these microcontroller boards. So Arduino Uno is one of the popular microcontroller boards. So it is very easy to use, and it is the coding in there is easy. So we have in internet we have multiple resources that provide us the sample codes and sample libraries libraries that enable us to implement some projects in these Arduino boards. So the IDE or the platform that they have provided us to do the coding is comparatively easy uh, when compared to other microcontrollers, and therefore it's easy for us to implement our code there and run it, and then we can implement that code in the microcontroller, and we can get the task done. So therefore this is a very popular microcontroller, right? So we can we need to use certain like specific languages to implement codes in these controllers. For example, in Arduino we are using C++, and then we are having so we need to use that language in order to implement the code in there, right? So we need to follow their standard method of coding, and then their sample way of writing the code, and then we can get the output that we want. And the microcontroller used in there is at mega 32.8p and so on, right? The clock speed is about 16 megahertz, and the Arduino is good for many things, but one main advantage is that it is having a limited memory. That means its memory is in kilobytes. So this is not enough in some cases for like large amount of data storage. So because of that, this is only used for like small scale data collection and maybe testing. So because of that, this Arduino board may not be the suitable option for cases where we need high amount of data storage and data collection and transmissions. Then we have another microcontroller that is known as Node MCU. So Node MCU is a low cost microcontroller, and it is having open source libraries, and it is easy to port. This is also kind of a popular hardware controller board. Its programming is done using Lua programming language, and then its microcontroller is based on ESP8266, right? So this is having Wi-Fi enabled module such that you can connect to the Wi-Fi using this. And then this is having two processing cores. So because of that, you can do the processing fast in this microcontroller. So actually, exactly in industry level IoT projects, depending on your application, you need to select the I think the correct controller board. So actually, as I know, like ESP32 is the most popular microcontroller board nowadays for applications like home automation and remote monitoring, and for cases where we are monitoring gardens and remote locations from our homes, and so on. So exactly, I do not know in industry the exact board that is used, but overall worldwide, ESP32 has become most popular microcontroller board. So maybe one reason is that ESP32 is supporting it's supporting many communication technologies, while also it is a cheap option. Like when we are buying this is cheaper in terms of the price when compared to other types of microcontroller boards. So once I have seen that even in other countries, ESP32 is a very popular microcontroller board for their automation activities. So maybe in industry they have maybe much more like complex and advanced microcontroller boards than this. So as I said before, like IoT networks that we are considering in for this, generally we are considering about the small scale activities that we are doing at the edge level. But since in industry we are collecting high amounts of data over a long time, for that we need like I mean advanced amount of storage and processing. So based on that, we need to get more advanced microcontroller boards. So for low level, I mean, for smart automation at the homes and in our day-to-day life, we can use these boards, ESP32 and the other boards that I'm mentioning today. But in industry, I think we have much more advanced microcontroller boards for like large scale data collection and transferring. So depending on the application, the controller boards need to be selected. So if you have only small scale data collection and then you need to, monitor them timely with the time, then I think even ESP32 is sufficient for like small scale activities. So you need to, we need to refer the technical specifications of these microcontroller boards to specify like how much of processing is there in these boards, and then like what is the amount of data that it can transfer at some per time, and then about the amount of data you can store in the boards. So depending on the application, you need to decide which controller you need to use. And then ESP32, basically it has also two cores, just like the Node MCU. It supports Wi-Fi and it supports Bluetooth. So you can communicate using both Wi-Fi and Bluetooth, and it has more input output pins, and it is having inbuilt temperature sensors and Hall effect sensors. Hall effect sensors means like a sensor that can detect the magnetic and electric fields. So these sensors also can be used for situations where we are trying to sense the nearby objects and so on. So depending on the application, we can use these sensors to detect the environment and the conditions in the environment. The third last microcontroller board I'm going to talk about is the Raspberry Pi. So this is a very highly advanced microcontroller board. So maybe this, this can, depending on your application, you need to choose that, as I said. But this Raspberry Pi, controller board is good for like advanced activities. Like it can do processing inside the chip, and it can do image processing. It can do like it can detect images. It can choose images, like classify images. So that level of processing can be done at the Raspberry Pi. So because of that, this controller board is used for like complex tasks. And then it also has the like communication ports, like 4 USB ports, and it has different HDMI ports and Ethernet connection, onboard Wi-Fi, Bluetooth, and many input-output pins in the board, which allows it to have multiple sensing ability and communication ability. So it is a very actually, compared to other controller boards, this is expensive than the other three types of controller boards. And then therefore this is expensive, but in terms of performance, it is having high performance than the other uh, controllers. And also processing speed is higher, and also it is having higher storage, like 1 gigabits of RAM. and then 1.2 megahertz of clock speed. Also, it supports like Linux, Python, right? It allows us to develop applications inside the processor. So this has a high amount of functionality because it allows us to use Python and like Linux, and then build codes, and then do like different build some applications that can do some work. And because of that, at the microcontroller board itself, we can do some processing and do some calculations, and based on that we can make the decisions. So that is very useful in situations where we just allow the sensors based the node to make decisions on its own, and then only send the data that is necessary to the local server and the centralized processing server. So those were the basic hardware modules that I wanted to discuss about. So next we need to talk about the IoT protocols, right? So we were talking about the things or the smart objects of the physical design of IoT. Right, so the second part of the physical design of IoT is the protocols, right? So the protocols are the standards and the rules that define how the data is communicated uh, reliably over the link from the devices to the server, right? Or to the next network component, right? So the protocols allow us to form the standard of communication, right? So if we don't have a standard, then each device will communicate on its own in the way it wants, but it would be then not be comprehensive, or the receiver might not be able to understand what the data that the device has sent. So uh, therefore we need to, like, each device need to send the data in a certain manner such that the receiver can understand it. The receiver also can retransmit based on the data received using the same, or the using the protocols that are there. So the protocols help the devices to communicate reliably and send the data reliably from one end to the other end, right? So in IoT networks, we are using multiple protocols. I mean, there are many popular protocols that are widely used in IoT networks. So those protocols can be divided into application layer protocols, transport layer protocols, network layer protocols, and physical layer protocols, right? So we will be talking about these protocols one by one, right? So in the physical layer protocols, we are talking basically about the protocols that help us to send data reliably in the physical medium, right? Let's talk about the different types of uh, protocols that are available in the physical and link layer, right? So these protocols help us to provide reliable data transfer across the physical network link. So we have several examples: the Bluetooth, Wi-Fi, Ethernet, cellular, NFC, and so on. So all these technologies have a certain protocol, and they follow this certain protocol to transfer information. Right, so the Bluetooth is one such technology that is used in the communication in the physical medium. So it is now Bluetooth and Bluetooth low energy. There are two. There's a difference between the Bluetooth and Bluetooth low energy. So Bluetooth low energy consumes lesser power than the normal Bluetooth, and therefore it is also only used for short range communications. So the normal Bluetooth can have a range higher than the Bluetooth low energy. However, the normal Bluetooth is consuming high power. So for IoT applications, Bluetooth low energy can be used in situations where we collect data from sensors that are located in remote locations, and we are collecting information from those remote locations. So since we are targeting low power communications, low power consumption, wireless protocols, Bluetooth Low Energy is a viable option in that case. So we this Bluetooth is widely used in even in our homes when we are connecting our devices to other devices, right? So when we are using, for example, music like speakers or other devices that work with Bluetooth, we are using Bluetooth in our devices in our homes as well. So uh, the another one is the Wi-Fi communication technology. So Wi-Fi communication is very popular, and the protocol that is used to define the communication and the standards that should be followed is known as IEEE 802.11. So that is the standard that is collectively representing the Wi-Fi, the standards that should be followed in Wi-Fi communications. So there are subdivisions of this protocol. So based on different scenarios, there are different Wi-Fi protocol standards. So we have 802.11a, then we have 802.11b, then we have 802.11g, 802.11n, 802.11ac, and 802.11ad, and so on. These different protocol standards are there for different types of communication. So if we are transmitting in 5 gigahertz band, we can use this 802.11a standard, right? And then if we are using these standards, we can use 2.4 gigahertz, and then also some other parameter we can define for this standard. So once we are using a certain standard, uh, I mean, for the Wi-Fi communication, a certain specific, like modulation schemes, frequency of transmission, and the like method of transmission, all those things are defined, right? So once we are using these kind of like protocols, we need to we can operate using the specified frequency and specified modulation scheme, the specified uh, method of establishing the communication, and so on, right? So depending on our requirement, we use the specific protocol. So for example, if we take 802.11 AC, that is the advanced protocol standard when compared to 802.11a, which means that it can be transmit in both 2.4 and 5 gigahertz ranges, and also it can support like multiple input, multiple output communications schemes. That means multiple antenna communication schemes it can support. So once it receives data from multiple antennas, it can process using multiple antenna systems and decode the data. So this protocol is 802.11 AC is more advanced than previous versions, which are 802.11a, for example. So we can use the updated protocol standards or the previous protocol standards depending on our application. So 802.11 AD is used for 60 gigahertz band data transmissions, and then that is dedicated for like a high gigabit data transmissions. So once we are doing that kind of transmissions, we need to follow the standards of this 802.11 AD. So another communication technology that is used in IoT communication is the cellular mobile communications. And so there are many generations of mobile communication: 2G, 3G, 4G, and so on. So in all these standards, they have defined different protocols that should be followed in communicating and establishing communication uh, and transmitting data. So we can have data rates from 9.6 kilobits up to 100 megabits per second using cellular communication technology. So all the standards are defined they have in by their organizations like 3GPP. So they define like how the communication should happen. So every aspect of communication is defined by them by when they introduce these generations of mobile architectures. So once they are introducing 4G, for example, they are introducing all the protocols that need to be followed when doing the communication. So if now in research and in universities, even in industries, once we are implementing or once we are researching on these technologies and the protocols, we might sometimes observe that the protocols are having some missing information or some missing standards. Then we propose some new standards or additional updates that need to be done in the given 3GPP, for example, standard. So we can propose that into these organizations. So once we do that, also get they discuss and they update the protocols. So the industry, university, they both can propose updates to these standards to improve the communication reliability and the performance of communication. We can also, another type of communication technology that is used is LoRa communication. So LoRa communication is used for long range communications. LoRa means long range, right? So this has been introduced in France first, and then it has become popular. So long range communication is widely popular for IoT applications, and especially because this is a low power communication technology, right? This technology is low power and long range. So therefore, it is like there are several LoRa modules that are available. So depending on the module that you select, you can decide the range of the LoRa communication and how to what length it will get communicated. So so we can have like 8 to 15 kilometer range communication using long range wireless communication technology, and it will follow the LoRa uh, LoRa communication. So it will follow the protocol LoRaWAN protocol, which is in the which is defining the network layer activities, while also like LoRa technology is operating in the physical layer, right? It is operating in the physical layer, so it is used for communicating the data from the edge devices up to the gateway node, right? So LoRa technology and LoRaWAN technology are in two layers. So this is in the physical layer and this is in the network layer. So network layer activities are done by the LoRaWAN protocol. So LoRa technology is governed by the LoRa protocol. So it is defining how the physical layer transmission is done. What are the parameters that need to be followed, and what are the necessary frequencies that it needs to follow when it is transmitting is defined at the physical layer. So the frequency range it needs to follow, and the duty cycle that it needs to follow in that it is transmitting its data, it needs to be defined in the physical layer, right? So LoRa and LoRaWAN are two different protocols, and LoRaWAN is in the network layer. LoRa is in the physical layer. So LoRa is operating in the physical layer. So LoRa is a very popular protocol. So I will actually share with you a video, if you like, about LoRa technology that is in the internet, that gives you all the information about the LoRa technology. So LoRa technology is specifically used for long range communications for IoT systems. So as we are talking about IoT systems, it is very important to know these unique technologies that help in the IoT communication. So LoRa is one of those communications that have long range communication, and it has inherent technologies that it use to reduce the power consumption while also doing some reliable data transfer. So they are using technologies such as spread spectrum, and they are using that technology to use a wider bandwidth to transmit data while using low power over that bandwidth. Also, we have next the Ethernet communication. So the Ethernet communication is following protocols uh, under the standard IEEE 802.3. So under that protocol, we have several sub protocols, and depending on the medium that we are transmitting the Ethernet information, we have several standards. So if it is a coaxial cable transmission, it's 802.3, and if it is a copper twisted pair connection, it's 802.3i. And then if it is 802.3J, it is fiber optic communication. And if it is 802.3 AE, it's Ethernet over fiber. So depending on the connection or the transmission medium, right, we need to follow different ways of communicating the data, right? So if we are communicating using the fiber, for example, we need to use a different technology to transmit the data. The medium that is used is different. The thickness of the fiber cable is defined, right? So based on the standard definitions, these cables are manufactured for these communications, such that every industry is making in the same manner. Otherwise, each industry might make in different sizes, which might not be compatible in all scenarios. So therefore, it is this is very necessary to follow the protocols, these protocols, when we are constructing the materials for Ethernet connections, and then we can do. We can have the same parameters or dimensions in our transmission lines, and we can do the communication reliably. So we will now move to the next network layer protocols, right? So we talked about the physical and data link layer protocols, right? In the IoT protocols, we talked about the physical and data link layer protocols, and then we now move on towards the network layer protocols, right? So then we have the transport layer protocols and the application layer protocols. So we have a network layer. In the network layer, we have um, protocols, and these protocols are used for defining the standards for receiving and delivering packets reliably in the network. Right, so we are talking about packets in this network layer, or data packets, right? So these data packets must be following these IP addressing protocols, IPv4, IPv6, And then there's another protocol that can be followed is 6-low-pan protocol, right? So this 6-low-pan protocol is a protocol that can be used in constrained environments, right? So we will talk about that next. So internet protocols. So in the network layer, we have internet protocols. So these IP protocols, right? The IP protocols, internet protocols, IP protocols can be used to connect our devices to the internet reliably. And once a device is accessing the internet, it is given a unique IP address. And the unique IP address is given by a certain component in the network, right? So apart from that, these IP protocols perform the host addressing. That means the devices which are connected to the network we call as hosts. So we use these IP address protocols to give a unique address to each device. And it also allows us to route the packet from the source node to the destination node. The data packet that we send has the source and the destination address, right? So using those details and other additional details, the routing can be done from the source to destination, right? So the IP protocols or the internet protocols can decide, okay, in what direction this uh, how this data packet should be directed at each hop of the communication. At each hop of the communication, the the network component will decide after checking the network tables. There are routing tables at each hop, uh, and at each hop, that routing table, after checking the routing table, the packet will be delivered to the correct location or correct next hop. And then so those things are done by the internet protocols. So the IP, giving address to the devices can be done by different entities in the network depending on the scale of the network. So if it is a small home or an office, then the router can assign unique addresses to the devices connected to it. Right? So in that we use the protocol called dynamic host configuration protocol, that uh, that automatically assigns IP addresses to devices as they connect to the network. So this protocol helps us to give a unique IP address to each of the devices connected to the network. Then in larger networks, we have IP addresses defined to each device using a dedicated server known as the DHCP server. There's a dedicated server in the large networks to give unique addresses to each of the host devices connected to the network. And in IoT networks also, we have a DHCP server most of the time to allocate unique addresses to the devices. So there are basically two types of addressing protocols. So first one is IPv4 and the second one is IPv6, right? So IPv4 addressing scheme is a 32-bit decimal addressing scheme. So it only has decimal numbers, so numbers from 1 to 9 in them, right? Each number is between 1 to 9. Right, so this is the IPv4 addressing format. So each number is between 1 to 9, and it is a decimal, it's given in decimal format as well for us to easily identify. However, in hexadecimal, I mean IPv6 is in hexadecimal address format. That means like in there we have both the decimal numbers and the hexa numbers. We have DB, the characters from A to E, I think. So we have like characters and numbers in here, right? So in IPv6 address format. So also we have in IPv6 address format, we have a semicolon in between these like number separations, like colons. So uh, the address, I mean the addresses are denoted differently in this IPv4 address format and IPv6 address formats. So we can easily identify the different format by looking at the IP address, right? We can see that this is all decimals, so it is IPv4 address that is given. So IPv4 is uh, an addressing scheme which can only provide 4 billion unique addresses, right? That means like 4 billion unique addresses when it was very earlier in the history, it was enough, right? But now it's not enough to uniquely identify each of the devices in the world, because there are many devices in the world. So this is not enough. And therefore, IPv6 was introduced, which can provide 340 under-zillion addresses. That means 1 into 10 to the power 36. 1 into 10 to the power 36 devices can be named using IPv6 address scheme. So therefore, IPv6 address scheme is used currently that can name any amount of devices. So it is known, it is seen that we don't need other type of addressing schemes now, because this can address all the devices. Apart from that, once a device is connected to the network, after some time, the DHCP server can, I mean, even change your IP address. That means that our IP address is not static. That means the network can change our IP address from time to time. So because of that, each device does not need to have a static IP address. So because of that, multiple devices can be, I mean, have, I mean, can change its IP address, and the IP addresses can be used multiple times, therefore, for different devices at different times. So likewise, we can have two. We have two types of IP addressing, and these are used to give a unique address to each device in the network. So we have the IPv4 address. So it is a 32-bit address, right? So 32-bit means like in binary format. Right, so we have like in each, I mean, in each component in the IPv4 addressing scheme, we have like 4 numbers. We have 4 numbers. So in each 4 number, we can represent this as 8 bits. So 8 bits, 8 bits, 8 bits, and 8 bits, we have 32 bits. And then they are separated using a dot. And each separated number we call as octet. And each number of this octet can have a value between 0 and 255, right? So I mean, in this decimal format, it is like that. So it can be between 0 and 255. However, the computer only understand in binary format. When we give a IP address to the computer, it will convert its number, I mean, each of these numbers into the binary format, right? So each of these number we can use the standard 2 to the power format to give a number, equivalent binary number to the to these decimal numbers, right? For example, 66 is given by this binary representation. 94 is given by the second binary representation. Likewise, we can follow the procedure to convert the decimal to binary conversion. So you are, I think you have followed this net in the network layer classes as well. So one address that is allocated for that is not allocated to any device in the world is this 127.node.1. So this address is not allocated to any device in the world. This is used by each device to check its network connectivity and whether its network interface layer is correctly connected to the network. So once you go to the command prompt and then you type this number and you type ping and 127.0.0.1, you can get a message from the network that it is connected, or it gives us a like a give us a response without an error, right? So if it gives us a output without an error, then it is connected to the internet or the connection layers, right? So uh, we can actually you can try to do that as well. So and you can try to ping it in your computer and you can check what is the output that comes once you do that, right? So it is known as the loopback address, right? So it is used to check whether it's having the basic network setup uh, in it, right? If you get an error in there, that means you are not connected to the network. Right? So sometimes it might get an error, right? Request timed out or some response error or something like that. If you get an error, then you're not connected to the network. So in order to check whether your device is connected to the network, this is a possible way to check the connection. Right? So this address is a class A address. Right? So in IP addresses, we have different classes defined. Right? So by checking the first number of the IP address, we can say the class of that address, right? So this one has a value 127. So that is a class A address, right? So we will talk about the classes of the addresses. So we have five different types of IP address classes. So we have class A, B, C, D, and E, right? So these class addresses are defined for the IPv4 version only, right? Because IPv6 does not need this classing address scheme to identify the different IP addresses. Only in IPv4 address scheme only they have defined these kind of classes. So IP address is basically constructing of two parts. It's made up of two parts, the network address and the host address. So we have a certain uh, in our IP addresses, we have a certain range allocated in our IP addresses to define what network we are connected to. That one we are denoting as network ID. And the host ID is given from the rest of the IP address numbers, right? So host ID is defined using the rest of the bytes. So once we go to the class A, so we can see that we can identify class A addresses very easily. So anyway, class A addresses are used to identify large scale networks. Large scale means large number of hosts, large number of host devices. Right? When we have a large number of host devices uh, connected to our network, for example, in large company, it has a lot of host devices. So that company will take a class A address to I give IP addresses to each of its devices. So that a class A address will be allocated for a large company, and then in this scheme, since like the network address is only network address range is only allocated for the first byte during the first byte of the IP address. So because of that, only in this first byte you can define the different networks that can be connected as IP address class A. So uh, only 127 networks can be connected to class A, because we are considering that class A addresses will have a 0 at the beginning. So once we have 0 at the beginning and all ones in the next uh, byte, the remaining bits of the byte, we have 1 to 127, right? So only 127 networks are possible with the class A. So the remaining 24 bits or the 3 octets define the host ID, right? So that represent the host ID, or it is allocated to defining the host addresses or host IDs of the devices. Then it is easy for us to identify class A addresses if the number of the class A address is between 101 to 126. Right. So the reason that we are considering up to 126 here is because 127 is allocated as a loop address. Right. So we are not taking the number up to 127. We are only taking up until 126. So the first octet should be from 1 to 126. Then we can identify it is a class A address. Then also we can only host 2 into the power 24 minus 2 devices in this network. So it's almost nearly 17 million devices. The two addresses, the -2 here comes from separating from two addresses which are separated in the class A address uh, range for network identification. The first address is allocated for network identification, and the last address is allocated for broadcasting purposes. So if some broadcasting message needs to be transmitted in the network, this common like IP address is used. Then we have the class B addresses. So that address can be used for medium scale network. So in order to give IP addresses to medium scale networks, where we have 2 bytes of host ID addresses. So we have that amount of host ID addresses. That means 2 to the 16 minus 2 devices can be uniquely identified given IP addresses. That means 65,534 devices can be given IP addresses using class B addresses. And the first octet of the IP address should be between 128 up to 191 to be identified as a class B address. And then class C address. So class C address is identified using if the octet is between 192 to 223. So it is used to give unique IP addresses to a smaller network. It can only host up to 254 devices, right? And then we have the class D address, right, where the first octet is from 224 up to 239. This is used for multicasting purposes, right? So the devices who want to do device to multi-device communications, that means one device is communicating with multiple devices at once. Then all these devices, the transmitting device and the receiving device, must allocate for themselves a multicasting device in the class D. Therefore, this range of IP address is used for multicasting purposes. Then we have class E address, which is reserved for specific applications such as in the military applications, military communications, and in research activities and so on. In there, the first octet is between 240 up to 255. So we can identify such numbers, IP addresses using this octet only. I mean, using the integer that is there. So we can now we can actually do a small task. So can you let me know what are the class types of these IP addresses? I will try to type this in the chat. You can put in the chat what is the result of all these, I mean, addresses in order. Right. So sorry. Yeah, first one is class A. So it is, yeah, we can see that it's 10. So second one. So we can follow like a table like this, right? Once we want to clarify the classes. So you can look at this and you can let me know the classes of the addresses I have given in the previous slide. So yeah, so the second one is class C address, right? So it is 192.168 points. Yeah, so the third address is from class B, right? And then we have fourth one, it is 240, so class E. Then fifth one, it is class D. Yeah, it's correct. So we can define each class using the first integer of the IP address. And then we will talk about the IPv6 address scheme and what are the definitions related to that. So in IPv6 address type, we have 128-bit hexadecimal address, right? So when we convert the IPv6 address to binary format, there's 128 bits included in there, right? So each, this IPv6 address has like how many? Like 8 quartets, right? We call this individual component in here as a quartet. And we have like 8 quartets like this, and each quartet we can represent each of the numbers of these quartets. Inside the quartet we have 4 numbers or characters, right? We have both characters and numbers, and each of them we can denote using 4 bits. Likewise, we can denote each of the quartets using like uh, like 16 bits, right? So we can represent using 16 bits a quartet, and then we can have finally 128 bits. So likewise, we have the IPv6 address scheme. Right, so now we will talk about the 6LoWPAN protocol. So it is known as IPv6 over low power wireless personal area network. So this protocol is used for IoT applications, right? I mean, this is very useful for IoT applications. Right? So one thing is that it is used for low power, low bandwidth wireless sensor network communications, right? So these requirements are necessary or useful for IoT networks, right? Because as I said, we are talking about energy limited scenarios and communication resource limited scenarios. So because of that, we are targeting these low power, low bandwidth communications, right? So 6LoWPAN is a protocol that is targeting this energy constraint constrained environments. Right, so it is built for constrained environments, and it allows. So it is using a technique to reduce the data packet size, um, which makes it very low power communication and low bandwidth communication, right? So in that protocol, we have the IP header compression, which means that the IP header length is compressed such that the packet size is made smaller. In maximum standard communications in IPv6, we have 1024 bytes total length for the packet. But in 6LoWPAN, it is only 127 bytes for a packet. So the packet size is made significantly smaller, and therefore lightweight communications can happen, can be done in this protocol, using this protocol. So we can take a scenario, right? We can take a scenario that communicates using this 6LoWPAN technology, and we can consider how it happens. Right? So once assume that we have some sensors which are connected to each other, right? So these are sensors, let's assume. So they are collecting some information from its surrounding, and it is transferring its data to its nearby sensors, right? Using IPv6 addressing scheme. So 6LoWPAN is known as IPv6 over low power wireless personal area network. That means it is using IPv6 addressing scheme to communicate between these two sensor nodes, right? So that is why it is known as IPv6 over low PAN network. And it is using IPv6 addressing, and it is using IP header compression technique. And because of that, the data packet size is made smaller, and is used for constrained environments like energy constrained environments. And it is used in mesh network of sensors. That means like these sensors are communicating without the uh, support from the main network, right? It is not connected to the main network. It is communicating with each other in short range communications, and it is transferring data to each other, and then it is also forwarding the data towards the network infrastructure. So for cases where we like monitor like environments in remote locations, these sensors collect the data and send those data to the network, right? So this edge, at the edge of the network coverage, we have edge router, right? So edge router here like performs as the gateway that collects all the data that is coming from the sensor nodes, and convert that network protocol into the other network protocol, or connect the one type of network to the other type of network. So the edge router is uh, translating the network protocol from one type to the other type, and it is allowing the data to transfer from one network to another network. And once it is going after the edge router, the data is transmitted using IPv4 and IPv6 normal addressing schemes. So in the normal procedure, the communication happens after the edge router. Until then, it is using the 6LoWPAN protocol, where the communication will happen only using IPv6 addressing scheme, up until where the data receives at the edge router. So in here, the communication between these sensors can happen using short range communications like Zigbee, Wi-Fi. And these can be used for applications like smart meters, smart monitoring in remote locations, and in smart home applications. So specified IoT gateway is not needed. Edge router can perform as a gateway. And then we are now coming to the next layer, which is the transport layer. So in the transport layer, now we have talked about the physical and link layer, and then we have talked about the network layer. So we are now coming to the transport layer, right? So next we have to talk about the application layer. So in the transport layer, these protocols help the data packets to form a reliable link from the source to destination, and like transport the data packets from the source to the destination, right? So there are mainly two types of protocols. One is transmission control protocol, or known as TCP protocol, which is a connection oriented protocol. So which means that it is establishing the connection path or the communication path from the source to the destination before exchanging the data, such that the data is reliably sent from the source to the destination. And so the error of the communication is less and more reliable communication is done in here. So for example, once we make, for example, a request to the, once we send a request to the internet using, for example, HTTP protocol, then our communication is established using TCP protocol, because the website details must be sent to us reliably, and it should not be lost. However, UDP communication, user datagram protocol communication, is also widely used for different other applications, where we need low latent data. We need fast data. However, in here, in this protocol, the delivery of the data is not guaranteed. That means sometimes the data might be lost in the network. But this UDP protocol uses multiple transmission technology. That means it is sending the same data multiple times to the network. So because of that, the ability for the data to be lost is less. However, this is used in multiple scenarios where we need like low latency, communications, like very fast communications, like online data streaming. That once you are watching a video, we need like real time updates about the video, right? So because of that, UDP is used for online streaming. So one of the reference books that I recommend for this course is like Internet of Things, a hands-on approach by Arship Bhagia and Vijay Manchetti. So this book is okay for IoT. If I find some other resources, I will upload in the LMS. Right. So I would like to give you some questions to try out. So can you try to answer these questions and then let me know, like, for example, for the answer for the first question, right? So how does using simpler protocols benefit IoT networks? So if you know the, uh, answers, you can let me know in the chat. Yeah, so the advantage of using IPv6 in the 6-low-PAN networks, I believe you're asking. So, uh, so IPv6 is able to like um, address any type of um, any number of devices. So one thing is that, and then it is more like you can fix the addresses for each of the devices in the sensor network using IPv6. Sometimes IPv4, we constantly change the address of the device. So according to my understanding, that is why IPv6 is used in the IPv6 wireless network protocol, 6-low-PAN. It's because like IPv6 addresses, there are certain addresses that we can allocate it for these and the constraint network communications. So according to my understanding, that is why IPv6 is used because we can separate out a certain addresses separately just for that application. Just for 6 low pan communication we can allocate, but IPv4 we cannot allocate like that, because as I said before, IPv4 addresses are not enough. So they can be changed all the time, and then because of that, the communication, the I mean, we need to like always inform the transmitter or the receiver about our change in IP address and so on. So it is difficult once we have different IP addresses. So that is according to my understanding. That is why IPv6 is used in IPv6 low pan. So yeah. So the first question is about the using simpler or less complex protocols in IoT. So one answer is, yeah, the energy efficient. It is energy efficient. So yeah, so once we use low complex protocols, that means the processing that needs to be done by our sensors and our processing boards and all the communication schemes is less, right? So the nodes don't need to spend uh, much energy, right? Apart from that, another parameter also is getting improved, right? So what is another parameter as you think? Like there are other parameters. Another parameter, can you let me know? Like speed, yeah, very good. The latency is reduced because not much time is done, not much time is spent on doing the calculations. The latency is reduced, right? Because of that, IoT needs these low complex protocols, right? Because IoT needs to give real time updates about the remote locations with, I mean, the defined frequency, right? So if we have to do a lot of computations at the sensor and the microcontroller level, we don't get the data on time. So the data that we will receive will be old, right? It won't be fresh data. So we want to have fresh data, updated data. So we need low latent communications. So we need to target using low complex but reliable communication protocols in IoT. Apart from that, one other advantage I would like to mention is that the network congestion. The network congestion is going to be relatively low once we have less complex protocols, right? So the congestion is happening mainly because if we have like multiple data to be sent and it is getting lost in the network, right? But once we have less complex protocols, since the data can be quickly transferred to the server centralized unit, then the data lagging is lesser and the amount of congestion in the network is going to get less, right? So that is, those are one of the some of the answers to the first question. The second question, as you think, what is the optimal wireless communication scheme for making contactless payments? Yeah, so near field communication, as I said before, we have two-way communication in the near field communication technology, right? So therefore, we have ability to authorize the communication or the payment uh, using our personal mobile devices when we are using NFC communication. So because of that, NFC is widely used for contactless payments. So it is more reliable than compared to RFID, QR code scanning, and so on. Right? So third question is, what is the cheap option out of RFID and NFC in Sri Lanka? So that is just a practical question I mean asking. I think this is just for you to investigate and find out and let me know, because I'm actually like trying to figure out like how costs, I mean, what is the cost of these technologies in Sri Lanka. So in other countries, the NFC technology is much more cheaper than RFID. However, in Sri Lanka, the status can be different. So I just want you to find out these details and let me know in the assignment, right? You are doing an assignment for this. So you can submit the answers to the assignment. So I would like you to go through the online stores that have this information about the prices of the RFID and the NFC tags, for example, and then you can let me know per unit what is the price and what is cheaper in Sri Lanka. And then you can let me know the websites that you found the cheapest one, right? And then we have different hardware processing boards, and you can take three or even more hardware processing boards, and you can mention what are the inbuilt communication technologies that are there in the processing boards. And then finally, I would like you to briefly explain like upcoming trends in future IoT networks. In the last class, I mentioned about upcoming future IoT networks and the technologies that are expected to come in the future. So we were talking about machine-to-machine communications, the digital twins, right, virtual environments, and then we were talking about internet of nano things, internet of connected everything, right? So these concepts are some of the future IoT trends. You can search about them and you can let me know and briefly explain those things in the assignment, right? So those are the things that I wanted to discuss as the interactive session in this class. And then we can do some like we can talk about the other assignments in the next class. So I have given so I will actually end the class now. I end the recording now, and I will explain to you if you have any questions or any doubts about how you have to submit assignments, and then